This is video 16.2. We're going to talk about the modes of radioactive decay in this video. What you guys need to make sure you have out is table N of your reference packet. So if you don't have your own, borrow one of mine, but you've got to be looking at table N as well as table O. Okay, those are going to be kind of the two big ones that we're going to be using throughout this whole these last couple of videos. So following decays that we're going to talk about occur in nature as a result of unstable neutron to proton ratios. So in the last video, guys, we kind of talked about that a little bit, how typically it's a 1-to-1 ratio. And then once they start to kind of get bigger, especially those heavy nuclei down toward the bottom, greater than 83, they get that imbalance and they will start to decay. Okay, so each element can have isotopes that will decay, which just means to break down and form new elements, because remember, here with radioactive decay, guys, we're forming new elements. All right, this is the only type of reaction we've talked about all year that forms new elements. Up until this point, we've just kind of broken bonds and formed new compounds, but we haven't changed the nuclei. Because remember, if you change the number of protons, you change the element. Well, that's what we're doing here. So the first mode of decay, and if you look on table O in your reference table, these are listed there. So you don't have to memorize these modes of decay. You just kind of have to know how to use them and apply them. Alpha decay. This is a transmutation whereby an unstable nucleus emits alpha particles. Alpha particles, guys, in this decay are products. Okay, they're products in the reaction, and the nucleus becomes smaller with less positive charge. Alpha emission is a characteristic of heavy nuclei. Okay. So again, especially atoms that are greater than 83, they're more susceptible to undergoing alpha decay. So what we can see from alpha decay, guys, over here, we have our what's called our parent nucleide. Okay, and then it forms a daughter nucleide. So make sure you're aware of these two terms. And then here's our alpha particle. Okay, so we had plutonium that was breaking down into uranium and an alpha particle. So again, with these modes of decay, they're giving off whatever the particle name is. And again, you don't have to memorize it. If you look on table O, alpha particle is the first one listed there. It gives you the notation. There's two different notations that it could be. It could be looking like this, and this is the more common one that you will see, but it could also be listed like this. But guys, you know, or should know, that, hey, the top number here is my mass number, and the bottom is the atomic number. Okay, so when we start to apply these, and we're going to do this here in a minute, the big thing you just got to remember is that the left side balances out with the right side. So charge and mass are going to be conserved on both sides of our equation. You'll see more about that in just a minute. So the big thing, guys, you want to remember with alpha decay, so this is something you need to make sure you know, the atomic number decreases by 2. Something you don't have to memorize because it gives it to you in the symbol. Okay, in the symbol right here, it gives it to us. The number of protons decreases. These two go together. Mass decreases by 4. Number of neutrons decreases by 2. But again, guys, you can do the math. The math won't lie to you, so don't try to memorize this. Just use the symbol that they give you. But anytime an element undergoes that, so these are actually the same reactions, just two different pictures of it. But you can see that, hey, alpha decay means that, hey, you get an alpha particle kind of that is formed. All right? So how do we do this? Okay, the big thing you want to remember, guys, is that we got to complete these problems where that the charge and mass are conserved. Okay, charge and mass are conserved, and this is going to be the same method for all the different modes of decay, except they're just going to be changing up what particles. So an alpha particle is here. So think about it like this in terms of a math equation. So you've got your total here equals your two parts. So the arrow, guys, is like your equal sign. Well, we got to make sure that the new mass is going to be equal out on both sides. So it's essentially like saying, okay, 4 plus what equals 220. Or, on the flip side, 220 minus 4 equals what? So this is going to be 216 is going to be our new mass. And our new atomic number on the bottom, 2 plus what equals 87? So that would be 85. Now you're going to go to your periodic table, and you're going to just figure out what element has atomic number 85. When you look that up, that is astatine. Okay, so this last week when we had our guest speaker, he showed you this equation, guys. This is it. You are doing it, but it's not as complex as it may seem. I want you guys to pause the video and to try this next one. Remember, this is still alpha decay, so one of your products is going to be an alpha particle. Doesn't matter where you write it, if you write it first or second, because it's addition. Pause the video, try to figure out what the other daughter nuclide would be. All right, so 222 minus 4, that's going to give me 218. 86 minus 2 is 84. And when I look that up, that is polonium, P-O. Okay? So, again, you don't have to memorize it. Look on table O, and it gives you the particle. All right, the next mode of decay is called beta decay. So this is where this is the decay by a nucleus where it loses a beta particle. Okay? Beta particles, guys, can look like this, or they can also look like this, with that beta symbol. Again, table O shows you this is the second particle that's listed on table O, and they're being emitted, okay, or produced. So again, when we talk about decay, these are products that are made, okay? They're products that are there. So the result is of a nuclear disintegration. Something said to undergo beta decay is also called a beta emitter. So just be on the lookout for that. Okay. So you could kind of go to this website, guys, if you wanted to, and you could kind of see a little simulation. But again, same idea as we were doing with alpha decay, except now instead of an alpha particle, it's a beta particle. One thing to know is, hey, look, this is a -1. Okay, because it's an electron that we're losing essentially. It's a -1, so in terms of your math, make sure you're on the lookout for that. But again, here's kind of the summary of what beta decay is. Atomic number increases by 1, number of protons increases by 1, mass stays the same, number of neutrons decreases by 1. So basically, a neutron becomes a proton. That's kind of essentially what's happening here in beta decay. Okay, so let's try a couple practice problems. If you feel comfortable and you want to go for it, go for it. Pause the video and then take a look at it. So here, same idea. We've got to make sure that the mass and charge are conserved on both sides. So the mass I'm going to start with, that's 32, because 0, no big deal. But this part, 15 minus a -1, is really, guys, adding 1. So 16 would be my new atomic number of my daughter nuclide. Okay, this is still considered to be the daughter nuclide, even though the atomic number is larger, okay, because it's what's being produced in the end. So when I look that up, that is going to be sulfur. Sulfur. All right, so I'm still under beta decay, so I'm going to just draw my beta particle in. Doesn't matter what order I put them in. You guys go ahead and try the rest on your own. All right, so 14 is my mass. 6 minus a -1 is going to give me 7, so now it becomes nitrogen 14. Down here, put my beta. Again, it doesn't matter where my beta particle goes, so that's why I kind of am moving it around, just to kind of drive that home. Hey, it doesn't matter which order you put them in. So 214 is my mass. That's an easy one. -1 and 82 minus -1 is going to give me 83, and that, when we look it up, is bismuth. Okay, pretty straightforward. Again, you don't need to memorize it because table O has these symbols for you. The third type of decay is called a positron emission. Positron. All right, sounds really weird and made up. Guys, basically it's a positive electron. So a positron is produced, okay, during the conversion of a proton to a neutron. So this is the opposite of beta decay. Okay, where a neutron is becoming a proton, now a proton's becoming a neutron. All right, so we can see, hey, proton, and to break it up, guys, keeping that mass and that charge equal, that's where we get a neutron. So that means this part, we have to get that positron piece. So it's the flip of the last one. Atomic number decreases by 1, protons decrease by 1, mass stays the same, neutrons increases by 1. So these two, beta and positron, are opposites of each other. Okay, so again, pause the video, try it. I think you guys are probably getting the hang of this by now, and then I'll go through it here in just a second. So my mass is going to be 37. My atomic number is going to be 18. That would be argon. So still positron emission because it hasn't told me anything different. So 81, and this is going to be 36, and that would give me krypton. And the last one here, I'm going to keep it here this time. 19 is my mass, and this is going to be number 9, which is fluorine. Okay? Now, notice also on table O, guys, you have the symbol for a proton, you have the symbol for a neutron. Positron is there, it's at the bottom. Okay, so they show you what those are. So if you ever forget what a proton is, say another question's asking you about it, take a look at table O. Also with a neutron. No reason why you shouldn't remember what a neutron is, because again, they give it to you on table O. The last type of decay or radiation, guys, are gamma rays. These are super, super high energy intensive pieces. This is what the Hulk was exposed to. Just a public service announcement. If you expose yourself to gamma rays, you will not become the Hulk. You will get cancer and die. So you never want to mess around with that type of stuff. Just like X-rays, you wear that lead vest, same idea. They have no mass and no charge. They're just energy, and that's what makes them so dangerous, okay? Because it's just high radiation, high energy, and that's this symbol right here. So that's also a byproduct of nuclear decay, all right? So let's just kind of... I'm going to pause this video, and we'll come back and fill in this table O piece together and kind of talk more about it.